Okay, we are at the second part of our fourth day or fourth lecture on cybersecurity, and in this part, I'm going to talk about this very interesting and short talk slash paper by Ken Thompson in 1984. This was his Turing Award lecture. He won a Turing Award this year, I guess, on reflections on trusting trust. So Ken Thompson is credited with the development of the early days of development of the Unix operating system, along with his colleague Dennis Ritchie. The Unix abstractions that we commonly find in almost all operating systems today, and we take them as the de facto way an operating system is written, were originally designed by people like him, and all the kind of ideas like processes, files, file descriptors, open read, write, close, fork, exec. And these are all kind of Unix ideas that still live on in modern operating systems, and so they were they're quite these were the contributions for which they won the Turing Award. But in his Turing Award lecture, he chose not to speak on Unix, but talk about this interesting observation or experience that he had, which he titles in his talk. His talk is titled "Reflections on Trusting Trust." So, before I talk about his talk, I want to introduce this concept of a queen. A queen is a computer program, which takes no input and produces a copy of its own source code as its only output. Okay. The standard terms for these programs in the computability theory and computer science literature are self-replicating programs, self-reproducing programs, or self-copying programs. So when executed, they're going to produce their own text. Now, such programs are possible to write in most programming languages. You can write such a program in assembly. You can write such a program in C. You can write such a program in Python. In fact, this one-line program that I show here, let me zoom in, is actually a queen. Okay, so this is Python. I'm not an expert in Python, but because the implementation of the Python queen was so short, I chose to use this. Please correct me if I'm misinterpreting the Python syntax anywhere. But the way this program basically says C equals, so C is the variable, equals. This whole thing represents a string within these single quotes, and inside this string you have C equals %R print C %%C, and then finally you invoke the print command on Python, which takes this string C, which is initialized in the previous statement, and assume it treats it as a format string and uses C as the first argument of that format string. So it's going to replace this %R with this whole string, with the single quotes intact. So when you execute this program, it's going to print this string C equals, and then %R is going to substitute this whole string there, and then the rest of the stuff as it is. And that's exactly what the original program looked like. And so this kind of a trick can be done for almost all programming languages, and these kind of self-reproducing programs are called queens. Queens, or these kind of self-reproducing programs are very interesting. First of all, they're interesting just for the mechanics of it. You try to write a queen, and I have never tried to write a queen myself from scratch, or maybe I have, I don't remember. But Ken Thompson claims that it's a great experience to try to write it yourself rather than having somebody tell you what it is. Okay, but now, so in programming lab exercises also, I give you an assignment where I ask you to change a queen so that it kind of behaves differently. So it will hopefully give you some experience on what writing a queen involves. But the interesting thing from a computer security perspective is that because this program can replicate itself when executed, that's exactly what you need for a program that kind of propagates itself, and that's what we commonly call a virus, right? It has this property of reproducing itself. And so that's why this becomes an important component of security discussions on security or security attacks in particular. Now, one type of security attack are what are called Trojan horses, right? So basically, you kind of compromise a particular piece of software such that you include some code that is your own, which is potentially malicious, into some well-meaning code, such that when executed, it does what you want it to do. So you can think of a virus as nothing but a Trojan horse, which Trojan horse basically means you are able to inject into certain piece of software your own code, which when executed is going to produce a copy of itself in some other code. And that's what it keeps doing and kind of self-propagating and kind of, and that's why it's called virus or viral or things like that. So this talk by Ken Thompson on reflections on trusting trust is going to use this idea of a queen, because it is going to install a Trojan horse and then going to use the queen to basically self-replicate itself. So let's look at this. Let's look at his talk in more detail. So I'm going to use some quotations from his paper because I don't think I can say it in better words. So he says, to what extent, this is one of the subtext of his title, to what extent should one trust a statement that a program is free of Trojan horses? How do you know that the program that you're using, that the browser I'm using, is free of Trojan horses? Perhaps it is more important to trust the people who wrote the software, because this is I guess this is going to be the conclusion of this talk as well. Can I take software from an untrusted person, review it thoroughly, and be sure, even though the person was untrusted, can I be sure that the software is correct? Hopefully, this talk argues that that's not going to be sufficient. And why is it not going to be sufficient? Let's look at that. So, taking another quote from the paper, the C compiler is written in C. What I'm about to describe is one of the many chicken and egg problems that arise when compilers are written in their own language. Okay, so C compilers are written in C most of the time. Well, LLVM is written in C++, but then I can argue that C++ compilers are written in C++. Right? So usually there will be some language whose compiler is written in the same language because for whatever considerations, either efficiency considerations or programmability considerations, etc., you will basically have these situations to be a common situation, that the same programming language compiler has been written in the same programming language. Okay. So here is an example of some code that can exist in a compiler, in a C compiler. So this code basically, is trying. So when we talk about characters, we talk about characters like A, B, C, D, E, F. But then there are these special characters like the new line character, the tab character, and so on. And to distinguish, to say that these are characters and not something else, we basically have what are called escape sequences, and say \n represents the new line character, and \t, for example, represents the tab character. And so the compiler needs to understand what this character is. So the compiler will have some code somewhere which will look something like this, which is going to get the next character here, and then it's going to check whether that character is a backslash or not. So notice that because the C compiler is written in C itself, to checking whether it's a backslash character also involves using this \/ escape. Okay, and then if it is not, then it just return the original character. Maybe it's A, B, C, D or something. So it just returns that. But if it was a backslash, which means it was an escape, then it checks the next character. And if it was again a backslash, then you return the backslash character. And if it was n, then you return the new line character, which is represented by \n. Okay, so that's what you would do. So this is again quoting from the paper, this is an amazing piece of code. It knows in a completely portable way what character code is compiled for a new line in any character set. So when I say \n here, I am not. It's a very portable way of saying it, because maybe in my character set, \n's ASCII value is, I don't remember what it is, but let's say it's 20. Okay, so in my character set it's 20, in your character set it's 10. Irrespective, if you compile it with your compiler, it's going to give my backslash n, this character here, backslash n, is going to give you 10, and if I compile it using my compiler, it's going to give me 20. And that's why it's a completely portable implementation of how this is. Okay, and it somehow knows. So who knows that backslash n is 10 or 20? It's the compiler that's going to compile this compiler that knows that backslash n is 10 or 20. Okay. If in a different character set, the ASCII code of backslash n was different, then we'll get that character set's value, and that is actually baked into the compiler that was used to compile this particular code or this particular compiler. Now, suppose we wish to add a new character, backslash t. Sorry, not backslash t, but sorry, my notes are actually a little. So backslash v. Let's say I was interested in adding a new character, backslash v, and let's say I was interested in mapping it to 11. Okay, so how will I do this in this particular compiler? Well, let's look at this code. Maybe the first thing I can do is I can add another if statement which says if the first character was a backslash and if the second character was a v, then return backslash v. But is this going to work? This is not going to work because this is the first time I've kind of created a mapping for backslash v to 11, and let's say backslash v is a vertical tab, as he kind of assumes in his paper. So backslash v is supposed to represent a vertical tab as opposed to a horizontal tab, which is represented by backslash t. So backslash v represents a vertical tab, and backslash v is not a standard thing. I'm kind of trying to introduce it now, and so my compiler doesn't understand what backslash v is. And so if I write this code in my compiler and I compile this using my compiler or using itself for that matter, then this is not going to work because it's just going to say, hey, what is backslash v? I don't understand it, and it's going to stop somewhere here. So what is the solution here? Write assembly code. Okay, anything else?
Write C code, but more detailed C code.
What will be the detail? So we can write C code, but more detailed C code, but what will be the detail? How will I change this code? So recall that I said that the vertical tab is supposed to represent the ASCII value 11. And what this represents is a character. A character is nothing but an ASCII value that it returns. Now, the reason I was using backslash n earlier or backslash earlier was because it's a portable way. I don't care what backslash n is mapped to. It could be mapped to 10 or 20. Irrespective of what it's mapped to, that's what is going to get picked up because the compiler already knows what that means. But in this case, backslash v, the compiler doesn't know what it means. So we need to tell the compiler. So maybe I need to, instead of saying return backslash v, I need to say return 11. But that is not portable, because I'm hard coding the value that backslash v is 11. Can you say backslash v? No, backslash is just going to be, so backslash is one character, which is backslash. And backslash v would be two characters. One would be the backslash, and then that would be a string.
Backslash is just for special characters, right?
Yeah. Okay, let me just quickly review this. So here's the thing, right? Backslash v is, let's say, 11. Backslash n is, let's say, 10, and backslash is nothing but, let's say, I'm making it up, but let's say it's 15. Okay, so backslash is nothing but if the character value is 15, then what's actually going to get printed on the string is just a single backslash. When it's 10, then what's going to get printed is a new line. Right? So if you say backslash v, that's actually a string of two characters. The first character being backslash, which is ASCII code 15, and the second string being v, the second character being v, which is ASCII code whatever it is, right? Okay, so we create a temporary non-portable implementation as follows. So we create a temporary non-portable implementation as follows, which checks whether if the second character is v, then we return 11. But this is no longer portable because let's say tomorrow I want to change the meaning or your character set is different, you want to map it to 12 or something like that, then this is going to have issues. Okay? But once the compiler, this is the interesting thing, once the compiler has learned the escape sequence through the non-portable implementation, we can go back to the portable implementation. So once you have compiled this compiler, which knows that \v is mapped to 11, you get a new compiler. And now you can change the original code back to this original code which says \v, and now compile this compiler using the previous compiler, and now \v will be interpreted as 11. Okay? So this is interesting because once you introduced what \v means, after that you can just refer to itself, its own knowledge, going back, in a kind of, it's self-referential in that sense. So this was the interesting observation he made. And this is a quote from his paper. He says, "This is a deep concept. It is as close to a learning program as I have seen. You simply tell it once, then you can use this self-referencing definition." Okay? So the same, so let's say you want to do, a different person wants to map \v to 12, and then he just compiles his own compiler, and then the same code for his ecosystem is going to give 12, and for my ecosystem it's going to get 11, and it's going to propagate itself. So the compiler that got created, we're going to create two different compilers. This compiler is going to treat \v as 12, and this is, although it's the same source code that we are going to compile, but because it was compiled by different compilers, the eventual compilers are going to be different because it's going to treat \v as 12, and this guy is going to treat \v as 11. So this is interesting, isn't it? I mean, source code is the same, compiler is different, the binary of the compiler is different, because once, like in the very beginning, somebody just planted a seed of knowledge, and it kind of remembers that knowledge and propagates the knowledge going forward. Okay? And that's why he says it's as close to a learning program as I have seen. Okay, so now that we understand this, now let's talk about the attack. Now the following represents a crude version of a compiler that accepts a string, let's say a program source code, and returns the executable code. So it accepts a string, which is, let's say, a C program, and it returns the executable code for that particular C program. Now let's say I wanted to plant a Trojan horse into the compiler and say, if you ever see the login program, then just accept this degenerate password or something like that. So this is how I do it. I basically put inside the compiler this extra code in the source code, and say if S matches a certain pattern, which checks for whether it's a login program or not, some kind of pattern, then you compile a bug inside it, which basically is going to allow you to get in, and that kind of special secret, that master key that's going to allow you to get in. So this is a Trojan in the compiler source code. But this doesn't look very exciting. I mean, if you just add this Trojan, anybody who looks at the compiler source code is immediately going to figure out, it's going to be, even a casual review of the compiler source code is going to show that, hey, what is this going on? Why is this Trojan here? And somebody is going to remove it. Huh? Pattern, is the pattern a regular expression or a dictionary? It could be anything. I mean, I'm not going into those details, but let's say either the name of the program or the structure of the program or some characteristic of the program, which basically allows you to identify that this is a sensitive program, and I want to allow a backdoor in this program. So I put that in the compiler source code. Now, even though the original program looks clean, the compiler obviously looks very, it's easy to figure out that this is a bug in the compiler, and hopefully this will get caught. So this doesn't look like a very powerful attack.
Just compile this so it won't get caught. Just compile this compiler so it won't get caught. I mean, like,
Yeah. So the solution being proposed is, let's just compile this compiler.
no one will see the source code.
So no one will see the source code. But no, I mean, let's say the people say that I want the source code of the compiler, and then I want to compile it myself. And then I'm going to use the compiled executable to do this. So, and before they compile it themselves, they're going to look at the source code. So in which case, they're going to look at the source code and find that there's a Trojan here, and they're going to just raise an alarm about that. Okay, so that's not going to work. But there's a clever idea here. Okay, the idea is you have two Trojan horses inside your compiler. The first Trojan horse checks for the login program, just like it was doing earlier. But the second Trojan horse checks for whether I'm compiling a compiler. And if I'm compiling the compiler, then I plant a second bug. And what is that second bug that I plant? That you emit this whole code, this whole the set of two Trojans into the compiler itself. So if you compile the login program, you insert the backdoor. If you compile the compiler, then you insert this whole code into the compiler. And that's exactly the concept of you use the idea of a queen to do that. So it's code that's going to self-replicate and put it inside the compiler itself. So in this, the second pattern matches to check if we are compiling a compiler. Further, the bug 2 that is inserted is a queen that contains both the Trojans as the payload. Okay? Once you have compiled this compiler into an executable, let's call this executable compiler the C compiler, or no, some C. I don't mean the C language compiler. Let's call it C, the compiler. You can now remove the Trojans from the compiler source code. Right? You can remove the compilers from the Trojan source, from the compiler source code. Now, because the executable contains the Trojans, when you compile the compiler, even without any Trojans, the source code looks absolutely clean. You can review the source code as much as you like. But when you compile the source code, the executable has already learned that you should insert the two Trojans inside the executable. And the Trojans will get inserted into the executable of the new compiler as well. And if that compiler compiles another compiler, it will keep propagating itself. So if you were able to contaminate the compiler even once and create an executable, and then you even remove that contamination, you got an executable, and that executable has learned what to do when it sees a compiler and what to do when it sees a login program. And now that executable will just live forever, and unless you are inspecting the executable, you will never identify the bug if you just do source code reviews, because the source code looks absolutely clean all the time. So once you have compiled this compiler into an executable C, you can now remove the Trojans from the compiler source code. If the compiler source code is compiled using C, then it will always have the two Trojans, even if the source code seems correct on manual review. Further, this perpetuates as the compiler has learned the Trojan, and so the compiler that you compile using this compiler will also have the same Trojans, and so on and so forth. And this is fascinating, isn't it? So what's the moral? So this is the quote from Ken Thompson's paper. The moral is obvious. You can't trust code that you did not create totally yourself. Especially code from companies that, so this is his words, not mine, especially from companies that employ people like me. Okay? No amount of source level verification or scrutiny will protect you from using untrusted code. In demonstrating the possibility of this kind of attack, I picked on the C compiler. I could have picked on any program handling program, such as an assembler, a loader, or even hardware microcode. As the level of program gets lower, these bugs will be harder and harder to detect. A well-installed microcode bug will be almost impossible to detect. Right? So if you are a security agency and if you have leverage over what hardware a particular popular hardware company is selling you, then you can install this and kind of, for that D-Day when you want to exercise it, you can exercise it, but otherwise everything looks fine and nobody's going to figure out what's going on, because as you go lower and lower, the level of complexity just becomes higher and higher. There are over billions of transistors on a laptop, and to figure out what those transistors are doing is manually impossible to review. Right? The higher you go, it's easier to review. And these kind of Trojans can be inserted at any level. And the lower you insert it, the harder it becomes to manually review them, but they still live on. Okay, so this is somewhat of an alarming situation. And that's what I wanted to say. But I would also give my own take, and this is also a shameless plug, that you can use our equivalence checker that is actually now available commercially through our startup called Compiler AI Labs. This is a joke. But basically what our equivalence checker does is that you can look at the C program and the executable program, and it will tell you whether the two are equivalent or not. So if there is a Trojan that the compiler is inserting, it will get caught by our equivalence checker. So at least at this level, between the C and the assembly program, this kind of attack is not possible, but it's still possible, let's say, at the hardware microcode level and things like that. Okay? So yeah, that's what I wanted to say, and yeah, we're done. Yeah. Thank you.